last week. Okay, we have learned about all the gas laws. Okay, so we have Boyle's law, Charles' law, Avogadro's law, and then we also have combined gas law. Okay, all right. So next we have ideal gas equation. From the basic gas laws that we have learned, okay, these three basic three basic gas laws. We have this ideal gas equation. Okay, so ideal gas is a condition. Okay, all right. In order to behave ideally, in order to become ideal gas, we have to ignore, okay, ataupun we neglect the attraction or repulsion between the molecule of gas. Okay, and then the volume of the particle, the gas particle, the volume of the gas particle is negligible. So we can just simply assume that the volume of the gas is the same as the volume of the container, right? Okay, so we have this equation that is known as PV-nRT, the ideal gas equation, right? Which can be derived from this gas laws. Okay, all right. So please take note that the R, the constant or the gas constant, the value is 0.0821. Okay, and this is the unit for the constant. And we also have 8.314 J mole negative 1, K negative 1. Okay, all right. So please make sure that you know when to use these two. Okay, all right. Normally, commonly, we would go for this 0.0821 instead of this one. But we do have formulas that we need to consider, that we need to use these values instead of this 0.0821 value. Okay, all right. So in terms of the unit, okay, make sure that you have the unit. In case you don't remember the unit, you can always derive the unit from the formula itself. Okay, all right. So it is PV-nRT. And then we want to know the unit of R. Okay, in order to know the unit of R, it is, okay, PVNT, right? And then T must be in ATM, V must be in liter, N must be in mole, and temperature should be in Kelvin. So this is the unit. Okay, so the unit can be derived from the formula itself. In case you don't remember, you can always use your formula, the ideal gas formula, as your reference. Okay, all right. Okay, and then we have learned that. Okay, so we have several checkpoints, okay, that we haven't discussed during our lecture last time. So we are going to do that now. Okay, all right. So let's start with checkpoint 5. Okay, all right. So I assume everybody has completed this checkpoint. Tolonglah buat. Bila saya kata buat, before we will discuss it next week, kata contoh, make sure that you have finished it. Okay, by the time we have our lecture. Okay, all right. So checkpoint 5. Let's check your answer with the working solution that we have in the slides. Okay, all right. A 1 times 10 to the power of 3 liter steel storage tank contain 88.5 kilogram of methane gas. If the temperature is 25 degrees Celsius, calculate the pressure inside the tank. Okay, all right. So we are going to use the PV-nRT. Okay, calculate the pressure inside the tank. So PV-nRT. So we want to calculate the P. All right. So you have all the information given in the question. So you just insert the values, okay, into the formula, and then you will get the final answer. Okay. All right. So the question is asking for pressure. So by right, your unit should be in ATM. How do you get ATM? Because you cancel out the other unit. So liter will be cancelled out with liter up here. Okay, Kelvin will be cancelled out with K -1, mole -1 will be cancelled out with mole. And you ended up with this ATM unit. That is why you are the ATM as your final unit. Okay, all right. So again, I would like to remind you, please make sure that you have your unit in the working solution. Okay, in the working solution, and also your final answer. Okay, all right. So that is checkpoint 5. Yeah, please make sure that you convert everything that need to be converted. Okay, in based on the unit of R. Okay, like kilogram, you have to convert into gram, and then like degree Celsius, you have to convert into Kelvin. If later you have pressure, you have to make sure that the pressure should be in ATM instead of torr, mmHg, or Pascal ke apa eh. Alright, so please make sure that you do that first before you insert into the formula. Okay, alright, moving on. Checkpoint 6. Sulfur hexafluoride SF6 is a colorless and odorless gas and commonly used as an insulator in electronic equipment. Calculate the pressure in ATM exerted by 1.82 moles of the gas in a steel vessel of volume 5.43 liter at this temperature. Okay, all right. So again, this is similar to the previous question just now. You are going to be using PV and RT, but this time around, yes, the question is still asking for pressure in ATM. Okay, all right. So you have everything ready. You just convert the degree Celsius into Kelvin, and you can insert into the formula. Okay, so mole will be cancelled out with mole -1, liter will cancel out with liter. This one Kelvin -1, and we have ATM. Okay, all right. Moving on, we have checkpoint 7. Calculate the volume in liter occupied by 7.40 gram of NH3 at STP. Okay, so at STP, you should know that the temperature is 0 degrees Celsius and the pressure should be 1 atm. So these are the conditions for STP. Okay, all right, so the question is asking for volume in liter. Okay, so there are two ways in order to solve this problem. One, the most common one, we will go for PV and RT. Okay, so R, we have the value already. So we have the T. Make sure to convert 0 degrees Celsius into Kelvin, which is 273 Kelvin. Okay, and then the N is also, we can get the value of N by converting this 7.40 gram into mole. Okay, and then the P is also known because the condition is at STP. That means the pressure should be in 1 atm. So we can calculate for V. Okay, all right. So you can calculate for V. That is one option. Okay, the other option, or alternatively, we can calculate using the information that we have already known. Okay, that is already known. That is at STP. Okay, at STP, we know that the volume for 1 mole. Okay, the volume for 1 mole of gas, in this case NH3, will be, what is the volume for 1 mole of gas at STP, guys?
22.4.
All right, thank you. Okay, so 1 mole of NH3 gas, okay, the volume is 22.4 liter. Okay, so we know this, we knew about this already. Okay, so we may use this as our conversion factor, right? So 1 mole, the volume is 22.4. This is at STP. This is only applicable at STP, okay? All right, so 1 mole, it is 22.4 liter. If we have this mole, 7.40 gram, okay? So what will be the volume. All right, so 7.40 gram, we convert this into, what do we call that? Into mole first, okay? So 17 gram of NH3 is the molar mass. So this is for 1 mole of NH3. Okay, so we convert this into mole first, and then we can use this conversion factor as our, we can use this relationship as our conversion factor, okay? Because we want the volume. So 1 mole of NH3 is equal to 22.4 liter of NH, right? So we are going to get the same answer. Mole, cancel, gram NH3, and we have 9.75 liter as the final answer. So we have two ways in order to solve this problem. This way ataupun the PVNRT way, or this second method. Okay, alright. It's actually the same lah, sama, because it is noted that at STP this is the volume. Okay, moving on. Right, so this is the answer just now. Okay, next we have ideal gas equation. From this ideal gas equation, we can determine the molar mass, the mass, and also the density, right? So meaning that we can use this PV and RT, we can derive this PV and RT, we can expand it in order for us to calculate for molar mass or mass or even density. Okay, you don't have to memorize this formula. This is for molar mass. Later on, we have density. Okay, so you don't have to do that. You can derive it there and then in order for you to calculate for molar mass or density. Okay, take for example, you want to calculate for molar mass, okay, or mass, PV and RT. Okay, so we know that N, okay, N can be derived into, can be further expand into becoming mass and molar mass, right? So PV, N is mass over molar mass, RT. So there you have your molar mass and mass. You can calculate any of these two lah. Okay, all right. This is for mass and molar mass. Perlu ke kita memorize? No, we don't have to. There's a lot of other things that you should memorize, but not this one. Okay, tak payah pening-pening kepala. Because if you memorize, boleh. It's not a problem if you decide to memorize. Okay, but I'm worried if in case somehow you nak silap, okay, instead of PV ni dekat bawah, okay, you terletak dekat atas. Okay, so of course that will cause problem lah. Right? So, you do not have to memorize this. Okay, boleh derive terus dari situ. Okay, next we have density kan. So, we know that density is mass over volume. So, we have this already in the PV and RT just now. Okay, all right. So, what we need to do is to rearrange them so that we have the mass and the volume need to be, dia punya dekat bawah ni, apa buat we call that, kat bawah, pembawah tu. Okay, tak kisahlah dia duduk dekat bawah lah. Okay, so we need to rearrange this so that it become M over V. So M molar mass, okay, will be transferred to this side and V will be transferred to the other side. Okay, ataupun you boleh je terus buat terus. Okay, P M M M R T over V. So we have M over V already. Right? So this is what we call density RT. Okay, we can calculate for density. Right? Okay, so this is an example. This is the density that I have mentioned to you just now. So it should be in gram per liter. Okay, because the molar mass is in gram. The mass is in gram because the molar mass is in gram. And then the volume is in liter. Okay, for PV and RT, the volume need to be in liter. So that's why it is gram per liter. Okay, all right. All right, so this is example also. Okay, all right, so next we have checkpoint 8. A chemist has synthesized a greenish yellow gaseous compound of chlorine and oxygen and finds that its density is 7.71 gram per liter at this temperature and at this pressure. Calculate the molar mass of the compound. Okay, all right, so you have to calculate the molar mass of the compound, and you can also insert the density into the formula, or you can extract out the mass from the density. Okay, alternatively, you can extract out externally, okay, extract out the mass from the density, and the mass you can insert into the PV and RT in order to get the molar mass. It's not a problem, tak ada masalah. Nak buat kat luar pun boleh, you nak terus masukkan dalam formula tu, semua dalam formula pun boleh. Okay, alright, so PV and RT just now. So we have PV mass over molar mass, right? RT. Okay, alright, so the value given is for density, so we can switch this V and mm, okay, to the opposite side. Mm naik dekat sini, then mass we have V, okay, RT. Okay, alright, so PMM, this is the same as what I've shown to you just now, saja je nak tunjuk lagi sekali. Alright, okay, so we can calculate for the molar mass because we have P already given, we have density which is 7.71 also given, R is a known value, and temperature, okay, you need to convert into Kelvin. And tekan calculator, dapatlah 67 gram per mol, 67.9 gram per mol. Okay, alright, macam ini sahaja. Okay, moving on to gas stoichiometry. Okay, gas stoichiometry is when the reaction involve the formation of gas ataupun use gas as the reactant or form gas as the product. Okay, alright, so stoichiometry is when we can relate the product and also reactant, okay, product and reactant and reactant. So we have the relationship that normally we got ataupun we obtain from the balance equation. Okay, so we have that relationship, therefore we can connect them ataupun we can relate them. So that is what we call stoichiometry. Okay, it's the same as what you have learned in maybe in XPM, maybe masa kita awal-awal tu, stoichiometry kita cannot run away from stoichiometry. Okay, mesti ada stoichiometry. But the different maybe in terms of the phase that are involved in the reaction. So sometimes kita ada solid. Sometimes we have a mixture of solid and gas. Sometimes we have solid, liquid, and aqueous. Okay, so they differ in terms of that information given, but the stoichiometry, the concept of stoichiometry is still the same. All right, so we have this contoh, we have discussed this already, okay, and this contoh as well, where the information is only given in terms of volume, okay, but we can equate that the volume is also the same as N. Okay, is also the same as mole. It is directly proportional. So we can use the mole given to be and convert the mole from the balance equation. We can convert into volume right away in order to find out the volume. In this case, dia nak cari volume apa? Volume of the oxygen. Okay, alright. Dia bagi acetylene. Dia bagi benda lain. Dia nak benda lain. Itulah stoichiometry. Okay, alright. Okay, so let's discuss checkpoint 9. Question 1, potassium chlorate. Molar mass is given. Decomposes to give potassium chloride, KCl, and oxygen gas. So this is the R, the constant given. Sorry. Okay, so first question, you have to write the balance equation for this reaction. So this is a decomposition reaction. That means we have a we have one starting compound, and it will degenerate or decompose into few products. Okay, all right. So KClO3, they mention here that it will decompose into potassium chloride and oxygen gas. All right, so potassium chloride and oxygen gas. So it should be O2, bukan O, Oxygen gas must be in O2 form. All right, and then kita balance out. Okay, all right. So KClO2, this sebab sini 3, sini 2, so kita tambah 3 kat sini, so it becomes 6. Okay, all right. So here kita kena tambah 2 dekat situ. So oxygen is now balanced. Potassium, however, dengan Cl is not yet balanced. So that's why kita kena tambah 2 dekat situ. Okay, and then always check your balance equation whether it is balanced or not. Okay, for the final step. Okay, balance, all right, so this is solid, this is also solid, and this is gas. Okay, determine the mass of KClO3 that must be decomposed to produce 1 to 6 liter of oxygen gas at 133 degrees Celsius and 666.8 torr. Okay, obviously these two need to be converted into Kelvin and also ATM respectively. Okay, you have to convert that one first. And then, okay, cuba kita tengok soalan. Determine the mass of KClO3. Okay, the question is asking for mass of KClO3. But the information, okay, the informations are given for oxygen gas. Okay, so these are the information for oxygen gas. All right, so the strategy is we have to go for oxygen gas first. Okay, we have to calculate the mole. Because kita nak ada connection with the balance equation later on, we need to have the mole. Okay, the coefficient in the balance equation can be also represented as mole. Yes, too. So we need to have the mole of oxygen gas first. Kena ada that one first. Okay, all right. So the information given will be used to calculate the mole of oxygen gas. The mole of oxygen gas. So this can be used. PV and RT can be used in order to calculate the mole. Okay, all right. So kita dah dapat the mole later. Dah dapat this one, mole of O2. Okay, and then we can use balance equation to find the mole of KClO3. Okay, this is from balance equation, guys. Then we can calculate the mole of KClO3 because from the equation, 2 mole of KClO3 will produce 3 mole of oxygen. Okay, all right. So kita dah calculate the mole of oxygen just now. So we can calculate for the mole of KClO3. Okay, and don't forget the question is asking for mass here. All right, so you have to convert into mass of KClO3. Okay, all right, done. That's all for this question. Cuba tengok. Okay, so this is A. Okay, so this is the part where you calculate for mole. Okay, mole, ATM cancel with ATM, liter cancel with liter here, K negative 1 cancel with K here, and then we have mole negative 1, transfer ke atas jadi mole. Okay, alright, so from stoichiometry, please use the dimensional analysis, guys. Okay, if I were to proceed further from here, so this is for oxygen, right? Okay, proceed further. Okay, down here should be mole of oxygen. Kalau pakai dimensional analysis, okay? Alright, so mole of oxygen. So this relationship we can obtain from the balance equation. Okay, from balance equation, 3 mole of oxygen will be produced from 2 mole of KClO3. Okay, all right, so this one will be cancelled out and then we are left with mole KClO3. Okay, remember the question is asking for mass. Okay, kita proceed further. Down here should be mole KClO3. So 1 mole of KClO3, the mass is 122.6. This is molar mass. Okay, all right. So you akan dapat the same answer. Okay, so those who previously memang dah pakai the conventional, bukan conventional, dimensional analysis, please guys practice using your dimensional analysis. Jangan pergi convert balik. Okay, pergi murtad balik, masuk buat balik cara lama. Practice guna your dimensional analysis. Okay, those yang rasa still nak maintain with your conventional method, go ahead, but please make sure that you have the unit. Okay, you have the unit all all the way through, okay, from the beginning till the end, sampai habis. Right? Okay, you kena ada this one, 3 mole, 2 mole macam ni, you ada connection. This is the relationship. Okay, don't just simply use macam ni, 3O2, 2KClO3. Okay, ni apa benda ni? What's the unit for this one? Unit apa? Gram ke, volume ke, liter ke, atau mole? Okay, please specify. You are referring to which unit? Are you referring to gram? Are you referring to liter? Ataupun you are referring to mole? So please specify lah kat situ. Alright? Okay. Conventional method, siapa yang pakai conventional method, please take note on this. Kita dah balik pada calculation. Okay, check point 9 question 2. Okay. Aqueous lithium lupa nak tanya. Alright, so far how are you doing? Guys, okay ke?
Okay, madam.
Okay, madam.
Okay.
Okay.
Saya punya suara boleh dengar clear?
Clear, madam.
Boleh.
Clear, madam.
Clear, madam.
Please let me know if there's any lagging ataupun somehow I got disconnected sebab I have problem connecting to the Wi-Fi, Asasi's Wi-Fi, somehow tak tahulah kenapa kan. But so currently I'm using my data. Okay, so takut dia terputus lah tiba-tiba, especially if I receive a call, dia akan kacau. Saya punya, dia akan kacau dengan dia punya audio dia. Okay, right, tak apa. So that one you guys please let me know. Okay, question. Aqueous lithium hydroxide, okay, solution is used to purify air in spacecraft and submarines because it absorbs carbon dioxide according to the equation below. Okay, alright. So this is another fact, interesting fact, okay, yang you should know. Lithium hydroxide solution is used to purify air in spacecraft and submarines. Okay, so this is an interesting fact. You tahu kan bila dia submarine maksudnya dia akan submerge in the sea, whereas spacecraft dia duduk dekat angkasa lah, okay, dekat space. So the thing about space dengan dekat dengan dalam laut, kita ada kita tak boleh simply breathe macam kita breathe dekat ground. Okay, macam kita sekarang. So they are confined in a space. Maksudnya dia punya space tu limited. Dalam kapal selam maksudnya dia punya space dia tu dalam kapal selam lah. Okay, maksudnya everything will be confined in a vessel. Okay, so dekat situ bila you confine, you breathe, you produce carbon dioxide. And then dekat dalam tu kan ramai orang kan. Okay, so if we know that if carbon dioxide is, the concentration of carbon dioxide is melebihi limit dia exceed the safe limit, it will cause harm to our body. Okay, macam you pernah dengar kan yang orang buka aircon, somehow dia punya aircon dia tu ada leaking kan, and then dia confine dalam kereta tu, tak buka tingkap and whatsoever kan, dia confine lah, okay. So tidak ada pergerakan udara dekat situ, so the increase in concentration of carbon dioxide. And then ada lagi satu lagi very dangerous, very harmful gas is carbon monoxide. Okay, alright. So when these two gas dia tinggi, so it will be dangerous lah. It's not good for the body. If tambah lagi kalau dia melebihi limit yang sepatutnya. Okay, alright. So dia kena ada strategi to remove the carbon dioxide from the kapal selam ataupun from the spacecraft. So how do they do that? Okay, in order for them to hidup macam biasalah dalam spacecraft, tak ada masalah dengan pernafasan and whatnot. Okay, alright. So one of the method is by using lithium hydroxide, because this lithium hydroxide has the ability to absorb the carbon dioxide. Okay, and then transform carbon dioxide into lithium carbonate. So later carbon dioxide punya concentration in the vessel will be lowered, will be reduced. So dia kena make sure dia ada safe limit dia tu, kena make sure it should be below the safe limit. Okay, kalau dia dah melebihi, itu yang berbahaya tu. Okay, alright, so menggunakan lithium hydroxide. So question, the pressure of carbon dioxide inside the cabin of a submarine having a volume of this. So this is the volume of the submarine, which can also be the volume of the carbon dioxide, because carbon dioxide tak ada particle volume. Dia follow the volume of the container or the volume of the vessel, which in this case, the volume of the submarine itself. Okay, kapal selam tu sendiri. Okay, so the pressure for this volume is 7.9 times 10 to the power of -3 at this temperature. Okay, alright. A solution of lithium hydroxide of negligible volume is introduced into the cabin. Okay, so the volume does not concern us because we want to deal with the carbon dioxide. Okay, that's why dia tak bagilah volume of lithium hydroxide. Okay, tak perlu pun, kalau dia bagi pun kita tak guna. Okay, so eventually the pressure of CO2 falls to 1.2 times 10 to the power of -4 atm. Right, so initial pressure of CO2 is 7.9 times 10 to the power of -3 atm. Okay, alright, so after a while, when lithium hydroxide has been introduced, the after pressure of CO2 falls to 1.2 times 10 to the power of -4. Nampak tak? Dia decreasing. It is reduced now. Okay, alright. So, determine the mass in gram of lithium carbonate. So, the question is asking for lithium carbonate produced in this reaction. Okay, produced in this reaction. So, you have to, macam mana boleh terhasilnya lithium carbonate? When lithium hydroxide reacts with CO2. Okay, alright. So, ni dekat sini ni, macam mana dia boleh reduce from 7.9 becoming 1.2? Okay, in the first place macam mana dia reduce? Because ada reaction between lithium hydroxide with carbon dioxide. Okay, because the carbon dioxide after is now reduced. So dia reduce tu dia hilang, maksudnya dia is already reacted with lithium hydroxide and producing lithium carbonate. Okay, alright. So to represent lithium carbonate, you kena ambil the difference between this pressure. So you kena minus this pressure dulu, because that difference in pressure represent, will later on will represent the lithium carbonate. Jangan confuse, saya tak kata benda tu adalah lithium carbonate, tak. Maksudnya carbon dioxide tu dia reduce sebab apa? Sebab dia dah react with lithium hydroxide to form lithium carbonate. Okay, so this is stoichiometry. So first you have to calculate for the difference. This is in terms of carbon dioxide. Okay, so you akan calculate for the mole of carbon dioxide. This for the mole of carbon dioxide. You tolak, okay, and then you have the P apa nama tu? Initial reacted, so left, CO2 left. Okay, you dapat PCO2 left. you dapat pressure kan. Tapi what we want is mole. Kita nak mole sebab later kita nak connect the mole of CO2 and the mole of lithium carbonate. Okay, alright. So you have the PCO2 after you have minus these two value, and then you can calculate for mole of CO2. And then from mole of CO2, you are going to relate with the mole of lithium carbonate from balance equation. Okay, and then you can calculate for mass of lithium CO3. Okay, so this is the strategy lah yang kita nak guna. But kat sini yang paling penting will be this part here. You bukan ambil mana-mana salah satu, kena pilih salah satu, tak. You kena tolak these two. Okay, in order to get the PCO2 yang digunakan, PCO2 left, dia tolak, yang tinggal. Ya, betul. Sebab yang dah digunakan tu, akan react to produce lithium carbonate. Okay? Alright. Kena faham yang tu dia punya apa nama tu, cara dia react tu. So this is what we call applied question. Okay. Jom tengok dia punya working solution. Okay, so this is the first step that I have mentioned to you just now. You tolakkan dulu and then you dah dapat the CO2, the different. Okay, the different in CO2 just now. So you nak cari mole of CO2. Okay, you nak cari the mole of CO2 and then you masuklah PPNRT. Okay, alright, so cancel out what need to be cancelled out. So liter cancel out with liter, Kelvin, and then you have mole. So this is the mole of CO2. So kita nak connect dengan lithium carbonate. Okay, alright, so this is 73 mole of CO2. Okay, so if we proceed further from the equation, 1 mole of CO2, it will produce 1 mole of lithium carbonate. Okay, alright, soalan nak in terms of mass kan. So mole lithium carbonate, so 1 mole, the mass is equal to, the molar mass is 733.8 gram. Okay, cancel out, this one also. So you have 5.4 times 10 to the power of 3 gram. Okay, those who are using conventional method, make sure that you have this. Jangan main terus saja 73 mole dah 73 mole and then terus darab dengan molar mass. Jangan buat macam tu. You need to have this stoichiometry part. Kena ada stoichiometry part. Even though it is a 1-to-1 ratio, you still have to show it. Okay, kalau tak, you kena tolak markah kat situ. Alright. Okay, so that is all for ideal gas equation. Okay, so next we have Dalton's law. Any question related to previous subtopic?
No, madam.
Okay, faham ya? Okay. Now let's move on to the next subtopic, that is Dalton's law. Okay, all right, so we have one learning objective for this subtopic. Make sure that you are able to define what Dalton's law is. Okay, define Dalton's law of partial pressure and use it to calculate the partial pressure of a gas and its composition in a gas mixture. So Dalton's law discuss about the pressure of gas in a gas mixture. Okay, I don't know whether you guys, I'm not sure whether you guys notice or not. Okay, previously contoh-contoh yang kita dapat adalah normally the gas would stand alone. Maksudnya dia independent. Tak ada campuran of gas in the same container. Okay, if you are dealing with CH4, then CH4 lah yang the only gas present in the container, ataupun oxygen just now, or CO2. Okay, so in the vessel ada CO2 saja. Dia I mean, other than that dia tak mention lah. Okay, so kita boleh assume that the only gas present in the container is CO2 for example, is oxygen. Okay, semua single gas sahaja. Okay, previously. So now we have Dalton's law. So Dalton's law, dia punya highlight is on the composition of the gas in a gas mixture. So what happened to the pressure, okay, and then what happened to the mole. So when we have gas mixture, ada campuran of gas, so automatically we will have the total pressure. Okay, we would have total pressure. Okay, so now let's look at what Dalton is. So Dalton's law is the sum of the partial pressures of all different gases, provided the gases do not interact with one another. The ideal gas is still applied in this law. Okay, remember ideal gas adalah condition. Apakah conditionnya? Di mana there's no intermolecular forces ataupun no attraction or repulsion, okay, between the gas molecules. That is one, and then the volume is negligible. Okay, all right. So that that condition is still applied for Dalton's law. Okay, all right. Dia cakap the sum total, the sum of the partial pressures of all different gases in a mixture is equal to the total pressure of the mixture. Okay, all right. Take for example, we have in the container. Okay, imagine we have a container. We have A. Okay, we have molecule A. We have gas B and gas C and so on. Okay, all right. So each one of these gas has its own pressure. Dia ada pressure dia sendiri. Okay, alright. That pressure is what we call partial pressure. Okay, alright. Kalau dia standalone, for example, kalau dia standalone, so this is A, and then this is B. Kalau dia standalone, kita panggil dia pressure A, because there's only A je dalam the container. We don't have B, we don't have C and others. Okay, alright. So this kita panggil pressure. Same goes to pressure A, and then we have pressure B and so on. Okay, when we combine A, B dengan C, dia jadi masuk dekat dalam container yang sama, it is no longer being called pressure. Instead, it is called partial pressure. Itu je term dia dekat situ. Tapi the pressure is still the same. Individually, kalau they stand alone or when they are in mixture. Okay, so they still sama. It's just that the term used is now different. It is partial pressure. Why is it called partial? Because they are all now contributing to the P total. Okay, so bila kita combine, kita akan ada P total lah. Because each one of them may have different partial pressure. So when we combine all of this, so by right we should have total pressure. Okay, so the total pressure is equal to the partial pressure. Kita panggil partial pressure. Okay, kita panggil pressure dah, kita panggil partial pressure. The term used is partial pressure because the partial pressure of A is contributing to the total pressure. Okay, partial. So it's equal to partial pressure of A plus partial pressure of B plus partial pressure of C and so on. So that will be your total pressure. Okay. Alright, so like I mentioned just now, consider a case in which two gases A and B are in a container of constant volume at constant temperature. Okay, alright, so if they exist singly, secara single, maksud individually, so there's only A gas, okay, and this is only B gas sahaja yang present. So this is normally we would calculate for the pressure, betul tak? Kita akan calculate guna PV and RT. Betul, tak ada masalah, boleh. Okay, provided the mole should be mole untuk A lah. Janganlah you calculate for partial pressure, for pressure A, tapi you guna N untuk B punya gas. Tak betul lah tu. Ini kena sama lah. Okay, baru dia represent the pressure. Okay, same goes to B. We can use PV and RT to calculate for PV. Alright, okay. If we combine this A and B, so dia ada mixture of gas here. So of course kita ada P total. So P total is equal to partial pressure of A plus partial pressure of B. Sebab dia dah combine kan. So it is called partial pressure. Partial pressure of A, partial pressure of B. So partial pressure of A can be used, we can calculate the partial pressure by using PV and RT. Same goes to PB. We can use this formula to calculate for PB. Sama saja. It's just that we want to highlight it is the total pressure is the sum of partial pressure present in the container. Okay, alright. So that is the first option. Cara yang kita akan gunalah since we have learned the PV and RT early on. Okay, alright. Alternative to that, we also can calculate the PA using this mole fraction. Okay, we can calculate for partial pressure of A by using this formula. PA is equal to mole fraction of A times P total. Okay, mole fraction of A times P total. So remember, so we have learned mole fraction in topic 1 last time. So mole fraction is equal to mole of A over mole total, which mole total is equal to, in this case, Na plus Nb. Okay, so this is what we call mole fraction for A times P total. Same goes to PB, okay, in order to calculate for partial pressure of P, okay, so we are going to multiply the mole fraction of P with P total. Okay, alright, so this is how you calculate for mole fraction. So there are two ways. Okay, mungkin some of you akan kata, tak apalah, saya prefer nak guna cara nombor 1 rather than cara nombor 2 because yelah, you've learned about PV and RT earlier kan, you dah tahu pasal PV and RT dulu kan. Macam you buat conventional method dengan dimensional analysis lah. Sebab you dah belajar conventional method dulu during your SPM time, you are comfortable with that. That's why you still nak pakai. Sebab dimensional analysis ni baru. You are not used to it. So you tak biasa. So you tak mau pakai. Okay? Bukan macam tu. Bukan case, untuk case ni dia tak boleh macam tu. Okay? It's not up to you to decide. It depends on the question. Depends on the information given in the question. Bukan, okay lah, saya tak nak pakai cara ni lah. Saya tak biasalah cara ni. Tak nak. Tak, bukan macam tu. You kena depends on the question. Sometimes question, instead of dia bagi RT, V apa benda, dia just bagi P total and mole. So can you use this method? Of course lah, tak boleh because you have less information in order to use this PV and RT. So you have to go for this formula. So in conclusion, you have to know both. Kena ingat dua-dua. Okay? Alright. So that is the formula lah yang kita akan pakai. Okay? Berkemungkinan kita akan pakai. Okay. Let's look at the example. A mixture of gases contain 4.46 mole of neon. A mixture of gases. Okay? So we have neon, we have argon, and then we also have xenon. Okay, all the moles are provided. Calculate the partial pressure of the gases if the total pressure is 2 atm at a certain temperature. So the P total is already given. Contoh like this one. Okay, we don't have the value for volume, we don't have the temperature, we don't have what else? Volume, temperature. We do have mole. Okay, so yang 3 tu kita tak tahu. So kita memang tak boleh pakai PV and RT. We have to use this one. P, for example, okay, P neon, mole fraction for neon, okay, times P total. So P total is no problem. We have that already. Mole fraction, to get mole fraction pun tak susah mana sebab the value is already in mole. So that, so 4.46 mole. Okay. So you kena tambah 4.46 plus 0.74 plus what else? 2.15. Okay. So all the unit are mole. So this one cancel sebab mole fraction is a ratio. Dia cancel atas bawah. That's why dia tak ada unit. Tapi P total we do have unit. Okay, alright. So, ialah times dengan 2 ATM. So this is for partial pressure of neon. So you dapatlah this one. Okay, alright. Okay, so checkpoint 10. Okay guys, please try to do this checkpoint on your own first. Okay, I give you like 3 minutes for you to complete this checkpoint. Okay, we will discuss later. Okay, cepat buat sekarang. Okay, all right. Are you done, guys?
Yes.
Okay, all right. So let's try answering this question. Checkpoint 10. Okay, exactly 8 gram of oxygen and 2 gram of helium were placed in a 5-liter tank at 298 Kelvin. Determine the partial pressure of each gas and the total pressure of the gas mixture in ATM. You also need to calculate the mole fraction of the two gases. Okay, alright. So ada tiga soalan kat sini. The partial pressure of each gas and then the total pressure, and last but not least will be the mole fraction of the two gases. Okay, ada beberapa, there are few ways in order to solve this calculation, to solve this problem. Okay, either way pun patutnya betul lah. Okay, right. Cara pertama, normally student would go for PV and RT. Okay, because we have the volume, we have the temperature, okay, we have the mass which we can calculate for the mole later. Okay, all right. So you can calculate for the partial pressure of oxygen and helium. So, okay, by using PV and RT. Okay, so please make sure that this is the mole of oxygen. This is the partial pressure for oxygen. And RT. Temperature tak ada masalah. R tak ada masalah. V of course tak ada because it's the same container. Okay, so you akan calculate, you akan dapat jawapan dia. And then same goes to helium. Okay, so you'll be calculating for helium using PV and RT. So the N is for the helium lah, the mole for helium. This is helium also. Okay, alright, so you akan dapat the partial pressure for each one of them using PV and RT. Last but not least, you akan calculate for P total, di mana you akan tambah PO2 just now, okay, dengan P helium. So normally student akan go for this method lah. Okay, alternatively, okay, you can also, then later you can calculate for mole fraction. Mole fraction tak ada masalah. Mole fraction, okay, for mole fraction ni oxygen kan. Oxygen macam mana? N of oxygen divided by N of oxygen plus N helium. Okay, masukkan saja, convert this one 8 gram into mole, 2 gram into mole, so you can insert into the formula. Dapat dah mole fraction for oxygen. Okay, right, so mole fraction for helium, N for helium divided by N oxygen plus N helium. So sama juga you akan dapat dah settle for mole fraction. So we have the partial pressure, we have the total pressure and also mole fraction. Okay, alright, alternative to this method. Ini mole fraction ni tetap dia akan kena pakai yang sama lah. Okay, you still need to use the same method in order to find the mole fraction. Okay, tapi to find out the P total, okay, alternative to this one, okay, you can start finding out the P total dulu. Cari the P total first. Okay, if you are using the P total, that means P total, PV and RT sama, you're going to be using the PV and RT. It's just that the N need to be the N total. Okay, the mole should be the mole total, which is mole of oxygen plus mole of helium. Okay, you akan dapat P total. So you akan dapat P total lah kat sini dapatlah P total. Dapat. Next, you have the P total. Dah ada P total kan? So you may use the second method just now, the mole fraction method yang tadi tu, yang this one. Yeah, this one. Second method and this one. Okay? Because we have the P total already. So this is first method, this is second method. Okay. So you can calculate for oxygen. P oxygen, partial pressure of oxygen is equal to mole fraction of oxygen times P total. Okay, so this one we have kat sini dah ada. Okay, so P total we have this one from the previous calculation here, masukkan saja into this formula, you will get the P oxygen, the partial pressure for oxygen. Okay, same goes to the partial pressure of helium. More fraction of helium, okay, times P total. So P total tu yang kita dah calculate. So siapa buat dua-dua cara pun betul, tak ada masalah. Cuma please take note you can also calculate the P total. Tak semestinya calculate satu-satu macam ni. Boleh calculate the P total. Cuma the N should be N total lah. Okay? Janganlah P total tapi N tu N helium saja. Tak boleh lah macam tu. Okay? Unless dekat dalam container tu hanya ada helium saja. So ini of course lah P total dia sama dengan P helium because helium is the only gas present in the container. So P total is the same as P helium. Okay? Dengan syarat hanya ada satu gas saja in the container. Barulah boleh the same as P total. Okay? Alright. So ini yang working solution lah just now. Okay? So you can calculate for the total pressure this way. Yep. Alternative to that, like I've shown to you just now, okay, tapi problem dekat sini dia tak tunjuk how to calculate the P total. Okay, dia tak tunjuk how to calculate the P total. So the P total is like what I've shown to you just now. Okay, and then masuk into this formula. Okay, next. Application of Dalton's law, okay, collecting gas over water. So we can use or we can apply Dalton's law in order to determine the amount of gas that we have produced from an experiment, for example. Okay, so for gases that is insoluble in water, such as oxygen, nitrogen, hydrogen, the amount of the gaseous molecule can be determined by collecting the gas over water and applying Dalton's law. Okay, all right, so we can use, for example, okay, you have a reaction. That reaction produce gas. Okay, and you want to collect the gas, you want to measure the gas, you want to measure the pressure ke, you want to measure the mole ke, whatsoever kan, you want to collect, basically you want to collect the gas produced. So how do you collect the gas? Okay, so one of the way is by collecting the gas over water. Okay, so this is also applying Dalton's law lah dekat sini. Okay, cuba tengok contoh Katakanlah this is your reaction. You react something dengan something lah and it will produce gas. Okay, produce gas. So you kena collect lah the gas. So you use this glass rod, glass tube, okay, in order to channel the gas produced, okay, into this water tank. Katalah ini water tank tu kan, you kena masukkan, submerge the tube di one of the end of the tube tu, okay, submerge dalam water and then you kena ada a test tube ataupun a vessel so that you can collect the gas. Okay, kena terlangkupkan dia tu supaya gas tu masuk dekat dalam this vessel. In this case test tube lah. Okay, alright. Syarat dia kena make sure that you are producing gas that is insoluble in water. Okay, barulah gas tu tak akan react dengan water ataupun dissolve in water, interact with water. So dia akan lalu je in water tu and then dia akan vaporize, dia akan goes into this test tube. Dia akan duduk dekat atas ni. This is where the gas is collected. Imagine kalau you produce gas yang boleh interact with water ataupun dissolve in water. Okay, dia tak akan keluar lah dekat dalam, dia tak akan masuk dalam test tube ni sebab dia dah kena tarik dengan water. Water held all the gases in supaya dia tak evaporate. Okay, that's why syarat dia yang pertama, you have to make sure that yang gas yang you produce, yang you want to collect must be insoluble, does not dissolve in water. Okay, if not sia-sia sahaja. Alright, so the gases product from a reaction, you produce gas tadi kan, is passed into a container of water. So dia akan lalu container of water. So this is the container of water. The gas in the water rises to the top since its density is lower than the water. So gas tu akan naik lah. Okay, dia akan bubble up. So dia akan remain dekat atas tu. Okay, because kenapa? The density of the gas is lower than water. So dia akan rose up. Dia takkan remain dekat water. Okay, so itu cara kita collect dia. The rose gas is collected in the inverted vessel, okay, as well as the water vapor that is produced by evaporation. So far, macam gas je collected, macam mana Dalton pula? Dalton kan is about a mixture of gas kan? Di manakah berlakunya mixture tu? Tiba-tiba jadi banyak gas pula dekat situ. Okay, di sini. Bila dia lompat naik ke atas, bila dia lompat pula, dia bubble, bila the gas bubble up, gas akan bubble up and then akan collect here, will be collected here. Okay, alright. The thing that you should know is, one thing that you should also know, not only gas sahaja yang collected, the water vapor will also be collected. Okay, water pun dia boleh evaporate jadi vapor. The reason it is called water vapor, okay, memang vapor dalam keadaan gas, tapi the reason dia panggil water vapor, not water gas, is because of initially it is water, okay, and then dia vaporize. Dia jadi gas. So that is why it is called water vapor. Okay, dia memang gas state, tapi nak menunjukkan that dia punya source initially dia from water, from the water surface, and then it evaporate and become gas. So that gas is what we call water vapor. Okay, so dia lain dengan oksigen. Oksigen memang gas. Dia tak ada oksigen water. Ada oksigen water, mana ada oksigen water kan? So oksigen gas. Bila cakap water vapor, so bear in mind, initially dia dalam bentuk liquid, then dia vaporize. So that's why vapor, water vapor. Okay, alright. Apa tadi? Kat mana tadi? So not only the gas, okay, is collected, we also will collect the water vapor. So dekat sini ada campuran lah. Dia akan ada P gas kita tambah dengan P water vapor. Sinilah, it's what we call Dalton'S. Inilah kita apply Dalton because it is now a mixture of gas. So satu kerja pula kan dekat situ kan. Kita nak collect gas kita tapi tercollect dengan water. Okay, but itu so far lah dia yang paling senang, most simplified experiment lah yang kita boleh conduct cepat. Okay, if not you kena ada devices lah, ataupun you punya eksperimen setup tu kena bombastic lah. Okay, kena ada machine and so that you boleh directly collect the gas. Yang ni antara yang cheap punya eksperimen lah. Okay, so tu cara dia apply the Dalton's law. Okay, so kita dah ada campuran pula dekat situ. So we have a P total which equal to P gas kita tu tambah pula dengan P water vapor. Right? But what we want is only for the P gas. Kita tak nak PH2O. Right? So how do we remove this PH2O? Kita ada this formula kan? So P gas of course will be determined later. So P total will be given. Okay, so PH2O is a constant. So anything about water, we should have the information. Okay, because water is a universal solvent. So normally kita akan ada information on water. Okay, alright. So vapor of water and temperature. Water vapor that mix with the collected gas is called vapor pressure. So of course water yang vaporize tu dia jadi gas kan, jadi vapor kan. Vapor tu adalah gas lah. Okay, so gas will produce pressure. Okay, it will produce pressure. So that is why dia cakap the water vapor dia akan produce vapor pressure. So the vapor pressure depends on the water temperature. Okay, so it depends on water temperature. So water can vaporize. Dia tak semestinya water tu vaporize dekat boiling point saja. masa pemanasan saja. No, tak semestinya. At normal temperature macam ni pun ada vaporization that take place. It's just that dia mungkin tak sebanyak kalau when the temperature is high. Okay, kata you nampak lopak air. You nampak lopak air pagi pukul 9. Pukul 9 pagi. Pukul 10, you nampak lopak air tu makin lama makin kecil. Okay, lagi tinggi temperature maksudnya it gets hotter kan, throughout the day. So, makin lama makin more water will be vaporized. Okay, so siapa yang masih tak tahu yang water boleh vaporize at any time, okay, at any temperature, so sekarang you patut tahulah. Okay. Okay, so the total gas pressure is equal to dry gas pressure plus vapor pressure of water at particular temperature. So we have this. Okay, look at the table here. So you are going to refer to this table. So nampak at temperature 0 degrees Celsius pun you have vapor pressure. Ada vapor pressure dia tu. Mungkin tak tinggi lah, tapi ada. Okay, so as the temperature gets higher, okay, become higher, the water vapor will also increase. Maksudnya more water molecule escape from the surface of the water and become gas. Naik ke atas jadi gas. So more water vapor, that means more pressure. Okay, more pressure tu yang jadi tinggi tu. As you can see, the pressure become higher. Okay, at 100 degrees Celsius, it will eventually be the same as the atmospheric pressure. Kita punya normal pressure, which is 760 mmHg. Okay, alright, so you are going to refer to this table. Okay, remember what we want is P gas. Kita nak P gas. So kita, in order to get the P gas, okay, you have to minus P total dengan PH2O. So H2O nak dapat dari mana? From this table. Okay, so once you have the P gas, you bolehlah hidup macam biasa using the PVNRT, cari mole ke whatsoever. Okay, alright. Okay. Let's look at this example. Oxygen gas generated by the decomposition of potassium chlorate is collected over water. Okay, the moment you see this statement, you can bear in mind that, okay, the pressure yang dia bagi tu, is actually P total, guys. Maksudnya, the gas will be mixed with the water vapor. Okay, so the total pressure yang dia bagi would be the pressure yang dia bagi is the total pressure sebenarnya. Dia ada cakap tak total pressure? Dia tak cakap, you kena sendiri tahu. Pandai-pandai lah. Okay, so the moment you nampak collected over water ni, you kena bear in mind. Dia sebenarnya P total. Okay, alright, so the volume of oxygen collected, dia nak collect oxygen sebenarnya. Okay, they collect at 24 degrees Celsius and the pressure 762 mmHg. Macam dia cakap oksigen punya kan? No, this is not for oxygen because it is collected over water. So this is P total, P oxygen plus PH2. Okay, so ini you kena extract out this P oxygen first. And then this is the volume, and then question wants the mass for oxygen in gram. The pressure of the water vapor is given, so it is 22.4 mmHg. Alright, okay, so dia nak apa tadi? Mass kan, dia nak mass kan. So later you akan gunalah PVNRT, tapi before that you kena prepare for the pressure. Okay, so you kena minus dulu. So in this solution, dia tukar satu-satu tu dalam ATM dulu, then baru dia tolak. Kalau saya akan tolak dalam mmHg. Okay, so P total PO2 tadi kan, PH2O. Okay, alright, so P total will be this one, dia dah bagi 762. So 762 mmHg tolak dengan PH2O berapa dia dah bagi? 22.4 mmHg. Okay, then you akan dapat dalam bentuk mmHg. Okay, and then baru you convert to ATM. 76 mmHg convert into 1 ATM. So you just convert sekali je lah. Nampak tak? You convert sekali je. Kalau dalam solution ni, dia kena convert, okay, P total dia convert dulu dalam ATM. Lepas tu H2O pun dia convert lagi dalam dalam ATM. So ada 2 step lah kat situ, leceh lah kan. Kita kan nak kurangkan conversion. Okay, lagi banyak steps you, sebenarnya lagi bahaya dekat situ. You have higher tendency to make mistake kat situ. Okay, but regardless, betul tak salah. Cuma step dia lebih sikit, tapi dia still betul. Okay, you have to have this. Okay, so it should be, remember you have to convert the MMHG into ATM before you insert into the formula. Okay, right. So soalan nak tanya apa ni? Mass kan? Mass, this one. Okay, so masukkanlah, dapatlah this mass. Kelvin. Mole -1 with mole -1. Liter with this liter. ATM with this ATM. And we have only gram left. Okay, that's why the unit is gram. Okay, alright guys. Tolong completekan this one. Okay, jom. Let's discuss. The reaction between carbon dioxide and water in the presence of energy from sun produces glucose and oxygen gas. So this is similar to the process of photosynthesis of a green plant, and the reaction equation is given as below. Okay, alright, so this is the equation for the statement mentioned up here. Okay, alright, so the question is, if the green plant releases 122 ml of oxygen collected over water at 743 torr and 20 degrees Celsius, calculate the mass of the oxygen and the glucose produced. Okay, dia kata kat sini collected over water. So please bear in mind the total pressure, bukan the P given here is P total unless otherwise stated. Okay, kalau dia nak cakap benda lain mesti dia bagi info lain lah. Alright, so in this case, the given pressure is the P total. Okay, because it is collected over water, that means the P total is equal to the P of oxygen plus P of H2O. So we want to remove this PH2O so that we can get the PO2 only. Right? Okay, soalan tanya, calculate the mass of the oxygen. Okay, we can, once we have the partial pressure of oxygen, the pressure of oxygen, okay, we can calculate for the mole and later we can calculate for the mass. Okay, from P oxygen, we can calculate for N of oxygen, okay, using PV and RT. And we can calculate for the mass of oxygen. Okay, alright. But the question is also asking for glucose dekat sini. This is what we call stoichiometry. Okay, that's the reason why the question give us this balance equation. Alright, in order to know the amount of glucose produced, you need this N. You perlukan the N of oxygen. Okay, because we can relate from the balance equation, okay, in order to get the N of glucose using balance equation. Okay, and lastly, we can calculate for the mass of glucose. Okay, so that's the plan lah. That's the plan. So basically, dia punya step to make sure that you have to minus this one. Okay, 743 torr minus with the partial pressure of H2O. So where can we get that one? So in this case, untuk slide untuk kita punya checkpoint, you have to obtain it from the table just now. Okay, alright. So it is at 20 degrees Celsius, right? So go check in the table at 20 degrees Celsius. The vapor pressure of water, okay, is 17.54 mmHg. Okay, we know that mmHg is the same as torr. 1 mmHg is the same as 1 torr. So kalau you ada 17.54 mmHg, okay, so the torr, in torr, it is also the same value. Okay. Okay, alright, so dah tahu tu, just ni lah. First step is to minus this one dulu, 743 torr. Okay, P gas in PO2, 743 torr minus 17.54 torr. Dapatlah in torr, betul tak? You dapat in torr, and don't forget to convert into ATM because you are going to be using the PV and RT. Okay, alright, so this is the first step. You have to minus. Okay, and then you can insert into the formula to find the mass. Okay, you can find the mass. So this is the mass of oxygen. Okay, alright, so next, dia nak tahu mass of glucose. Okay, alright, so this is what we have just now. mole of oxygen. Kalau saya nak proceed further kan kat sini, dia tak bagi tahu pula kat sini berapa. So this is for, so you have to find out the mole of oxygen, okay, in order to relate with the glucose, okay, from the balance equation. So this is mole of oxygen. Saya gunakan value ni, okay, from the balance equation 6 mole. This one lah, ni lah, okay, 6 mole of oxygen will react with 1 mole of glucose. Okay, mole of oxygen cancel out, so you akan dapat mole of glucose. Okay, so this is a mole of glucose. Ini saya just panjangkan je guna dimensional analysis. Alright, okay, and then you have to find the mass. You dah dapat mass, you kena ni mole of glucose kan. So nak cari mass macam mana? Times with molar mass. So here we have mole of glucose. 1 mole of glucose is equal to 180 gram. So cancel. So you have in gram of glucose. Okay, guna dimensional analysis. Okay. Alright. So, okay ke? How are you doing so far before we proceed to the next subtopic, kinetic molecular theory of gases?
Okay, madam.
Okay, madam.
Okay Alright, tak ada soalan So far tak ada soalan Wow. Tak ada langsung Tak ada Dia kalau tak ada soalan tu faham, bagus. Kalau yang banyak sangat soalan tapi takut nak tanya, tu yang tak bagus. Okay? Tanya. Rugilah awak tak tanya rugi tak tanya. Okay, alright, tak apa. Saya assume everybody understands, so we can proceed to the next subtopic, kinetic molecular theory of gases. So in short, it can also be called as KMT of gases. Okay, alright, so we have 3 learning objectives for this KMT of gases. Okay, make sure that you know you covers, okay, you cover all of these 3 learning objectives at the end of this subtopic. Okay, postulates of the kinetic molecular theory. So the word theory itself, okay, the term theory itself. So what are the theories for kinetic molecular that involve that? What is the theories in kinetic molecular theory for gases? Okay, all right. So theories or postulates or assumptions. So those are all the same, benda yang sama. Okay, sometimes we use interchangeably. Okay, berubah-ubah, but they are all carry the same meaning lah. Okay, maksud yang sama. Okay, theory number 1, postulate 1. Particle volume is negligible relative to the size of container. Okay, alright. So this is already known. Kita dah tahu that this one, because in ideal gas last time, okay, in order to be called ideal gas, the particle volume is negligible. We ignore the particle volume because they are too far apart from one another. Okay, alright. So kita ignore the volume, the particle volume, okay, and we just consider the size of the container as the volume of the gas. Kita assume dia bukan tak ada dia negligible, boleh diabaikan, boleh, it's not significant. Okay, dia bukan tak ada, dia ada, it's just that we neglect the value. Okay, postulate number 2, molecules move randomly in straight lines in all direction and at various speed. Okay, alright, so the reason they boleh move randomly in straight line in all direction and at various speed is because of there's no attraction or repulsion between them. Kalau diorang ada attraction or repulsion between them, they will not be moving in straight line. Bila dia langgar, dia mesti loss of energy, loss of momentum and whatnot. Okay, benda-benda macam tu. So it will not be moving in straight line. So the reason, okay, dia punya sebenarnya dia punya justification is because of there's no intermolecular forces. So that is why dia boleh move randomly in straight line. Straight line this ke sana, ke sini, straight line. Kalau ada intermolecular forces, it will not be like this. Dia mungkin akan macam tu ke, okay, dia turun ke macam tu, dia akan pergerakan dia tu differently. Okay, alright. So postulate number 3, the intermolecular forces is negligible. This one. This is the core. Okay, and then postulate number 4, when molecules collide with one another, the collision are elastic. This is again, dia punya reason being is due to this. Kenapa bila dia collide, the collision are elastic? As if macam there's nothing happen. There is no loss of energy kan. Elastic means dia tak ada loss of energy, speed dia still remain the same. Okay, it's just that dia bounce back tapi there's no loss of energy. That is what we call elastic. Kenapa dia macam tu? Okay, it's because of the intermolecular forces is negligible. Kita abaikan. Right? Kalau dia ada attraction tu, imagine bila dia collide, so dia attach. Bila dia attach, of course the energy and whatnot semua akan jadi different lah. Ataupun dia collide, dia bounce back but ada loss of energy. So that is what we call inelastic lah. Those two yang saya mention tadi. They bounce back tapi it's no longer the same as the initial state yang awal-awal tadi, sebelum dan selepas tu. Okay, for elastic sebelum dan selepas dia sama, tapi for inelastic dia tak sama. Okay, tapi for kinetic molecular theory, the collision are elastic because the particle does not have intermolecular forces between them. It's negligible. Okay, alright. So postulate number 5, the average kinetic energy of a molecule is proportional to absolute temperature. Okay, alright. So again, it's due to these intermolecular forces. Okay, so bila kinetic energy increases, bila temperature increases, the kinetic molecular energy also increases. Dia proportional. Okay, sebab kita assume dia tak ada attraction tu. Kalau ada attraction and whatnot, it will not increase proportionally. Mungkin increase sikit ke ataupun dia opposite inversely ke. Okay, so that's why it's because of the intermolecular forces. So normally kalau you try baca kan, sometimes KMT ni orang represent 3 postulate saja. Okay, sometimes people represent it as 5 postulate, dia banyak. Tapi at the end of the day, bila you baca and you know the reason behind it, you akan nampak, oh, that's why dia ada 3 postulate saja. Okay, alright. So as of now, let's just stick to 5 postulates that we have in the syllabus. So you kena tahu all these 5 postulates. Okay, make sure that you know in case the question asks, okay, state 3 postulates of KMT for gas. Any of those 5 will be your answer. Okay, alright, make sure dia jangan sama Okay, so this is the relationship of KMT to the gas laws. Nak menunjukkan that KMT ni dia actually align with gas laws. Gas laws like Boyle's law, Charles' law, Avogadro's law. Okay, so these laws are actually aligned with KMT. Dia bukan suka-suka come out dengan these theories. Okay, it's based on the gas laws that have been developed previously. So for example, we have Boyle's law kan. So for Boyle's law, kita tahu that pressure is directly proportional to the collision rate. So the more collision, that means the pressure will increase. Okay, lagi banyak pelanggaran cause the pressure to increase. Okay, and this is the KMT lah, dia punya collision rate tu kan. The KMT, the reason dia punya pergerakan, movement itu kan. And collision rate, which is this one tadi, collision rate is also directly proportional to number of density. Okay, it is the same as number of density. And the number of density is directly proportional to 1 over V. Okay, 1 over V. And at the end of the day, P yang initial tadi dengan yang ni yang dia buat directly proportional tu is directly proportional to 1 over V, which is Boyle's law. Betul tak? This is Boyle's law. Okay, bila dia try correlate all of them, dia end up P is directly proportional to 1 over V, inversely proportional to volume. So that is Boyle's law. Same goes to Charles' law. Okay, Charles' law, okay, we know that pressure is directly proportional to collision rate. Okay, all right, so this is the KMT lah. Collision rate is directly proportional to average kinetic energy. Bila kinetic energy increase, of course collision rate pun increase. And we know that average kinetic energy is directly proportional to temperature. Temperature increases, kinetic energy will also increase. Betul tak? And at the end of the day, the P is directly proportional to T. So this is what Charles stated last time. Nampak tak tally kan? So same goes with Avogadro's here. Okay, Avogadro's pun benda yang sama. Okay, collision rate with number density. Number density is directly proportional to N. Okay, with N, the number of mole. So pressure will increase when N increase. N increases, P also increases. So this is Avogadro's law. Okay, and then we also have Dalton's law for partial pressures for a mixture of gas kan. So in Dalton's, they mention molecules do not attract or repel one another. That's why the pressure can be maintained. Kalau di individually, okay, and kalau dia duduk dalam mixture, they have the same pressure. Okay, for Dalton cakap, provided sebab dia ignore the intermolecular forces, the attraction between the molecules. Kalau dia tak ignore, dia ada that intermolecular forces, of course, kalau dia individually dengan kalau dia duduk dengan kawan-kawan dia yang lain, it will not be the same. Okay, tapi sebab kita ignorekan other factor tu, so kita assume that if it exists independently and kalau dia exist with other gases, it will still be the same pressure. Okay, alright. So that is based on Dalton's law lah. Dalton's law ni pun ada dia cakap dalam KMT tadi kan, yang there's no attraction or repulsion between one another. It is unaffected by the presence of another gas. Tadi ada kan dalam KMT just now kan. So apa yang ada dalam dalam previous gas laws tu, okay, we have that in KMT. Okay, alright. Next is molecular speed. Okay, so molecular speed is important for gaseous molecule, okay, but not important for solid and liquid. Because kenapa? Because solid and liquid, they do not dia punya movement tu are very limited because dia tak se-mobile gas molecule. Gas molecule are very mobile. Dia boleh bergerak ke kiri ke, and in fact they produce pressure because of dia punya collision, they produce pressure. So the higher the speed by right, the more pressure will be produced. So that is why speed for molecule for gaseous molecule is very important. It plays a role dekat situ. So that's why kita kena study molecular speed. Tapi tak bermakna untuk solid and liquid dia tak bergerak. Dia ada vibration, dia ada rotation, tapi it's not as mobile as gases particles. Alright. All the gas molecule in a sample can travel at different speed. We know that we are dealing with a lot of particles, gas particles, banyak gas particles. So of course they are not moving at the same speed. They are all moving at different speed. Sometimes ada yang sama, ada yang tak sama, tapi basically at different speeds lah. After all, dia punya direction are not all the same, betul tak? Dia tak bergerak, apa 1, 2, 3 bergerak. Bukan macam tu. Dia bergerak ikut suka dia lah, random. And then the distribution of speed follows a statistical pattern, the average velocity of the molecule. So since they are moving at different speed, kita tak boleh lah nak consider each speed of each molecule tu dia punya speed. Berapa banyak, berapa juta particles yang kita ada, berapa ribu particles, kan nak consider for each one of the particles punya speed. Okay, so that's why we go for average velocity to represent the whole, to represent the gas molecule. The average velocity, we can come up with one speed for that particular gas. That is called as average velocity lah. Okay, so the root mean squared method is used to calculate average velocity. So to calculate average velocity, that is known as mu, root mean squared. Okay, we have this one, this formula. Okay, so URMS, mu RMS is a type of average molecular speed equal to the speed of molecule having the average molecular kinetic energy. So we know that speed is directly proportional to kinetic energy. So when kinetic energy increases, the speed will also increase. Okay, alright. So this has something to do with kinetic energy. So sebenarnya dia daripada PV and RT tu, tapi dia ada cara nak derive dia. Okay, so since we are not going to cover it in this in our syllabus, so the best is for you to memorize this formula lah. Hafal lah this formula. Sebenarnya dia ada derivation, okay, macam mana dia end up with this one. Alright, just please take note on this. Tengok dekat sini. The R now is different. Okay, we are not using the 0.0821. Okay, instead we are using 8.314. J, K negative 1, mole negative 1. Because kenapa? Because we are dealing with kinetic energy. Because we are dealing with energy. So joule, okay, is one of the unit to represent energy. So that's why we use 8.314. Okay, and the temperature, as always, will be in Kelvin. Molar mass, guys. Nampak tak apa yang, cuba beritahu sikit apa molar mass yang interesting sikit kat sini?
Dalam kg.
Yes, it's in kg. Dia bukannya tersalah typo or whatsoever. It's in kg. That means you have to convert in kg. Okay, so dia ada cerita lah dekat belakang tu, the reason kenapa dia buat kg dekat situ so you kena convert into kg because normally we will go for gram kan. Molar mass kita tak usi apa pun kan in terms of dia punya unit. But this time around you have to convert into kilogram. Okay, without the conversion, of course your answer will be wrong. Okay, ini je yang the only thing yang kita usik the molar mass punya unit. Okay, alright, so let's look at an example here. Calculate the root mean squared speed of helium atoms and nitrogen molecules in ms negative 1 at 25 degrees Celsius. So the R will be this is the value of R, okay, that we are going to use. The molar mass, please make sure you convert 4 gram per mole into kilogram per mole. Okay, so convert this first and then only you use this formula. Masukkan dalam formula 3RT over molar mass and square root everything. Okay, alright, so that will be the ni lah. And then this one saya still consider lah you bagi ms negative 1. Sebenarnya you nampak tak dekat sini? Dekat mana ms ni tak ada. Sebenarnya dia dekat dalam joule dekat sini. And then they combine joule dengan apa? Joule ni dalam bentuk energi kan. Dia kan ada kg ms negative 1 ke apa tak silap saya joule ni. And something negative 2 ke apa kan. So the reason dia dapat ms negative 1 is from here. Okay. Tapi kita of course, kita tak, bukan nak belajar unit. Tapi along the way tu kita nak make sure dia steady. Kalau cerita macam ni, tak apa, it is allowed, okay, for you to have ms negative 1. But please have all the unit in this calculation. But for the final answer, you should have ms negative 1. Since we are talking about the root mean square speed, guys, speed. Okay. Alright, so saya benarkan lah. Walaupun kat sini, mana M dia kan? Sebenarnya dia datang daripada J ni. You kena expand. Baru you akan end up dapat ms negative 1 sebenarnya. Okay. Alright. Okay, molecular speed. Buih mulut. Okay, sikit lagi rasa. Alright, so sekejap, tengok sekejap. Okay. Molecular speed, Maxwell speed distribution curve. Okay, this is a special curve ataupun graph to represent speed of gas molecule. Okay, alright, as you can see, dia bukanlah macam normal graph yang kita ada straight line, kita ada curve kan. That would be the basic graph lah. Okay, graph macam-macam lagi bentuk. You tak pernah tengok nanti as you go as you study further, you akan observe banyak punya style of graph. Okay, so this is another example. This is what we call Maxwell-Boltzmann. Dia sebenarnya nama dia macam ni. Saintis yang discover je lah. Saintis yang discover this teori ni. Nama dia Maxwell-Boltzmann. Dia 2 orang. Silap saya 2 orang. Okay, so it is named after them, Maxwell-Boltzmann speed distribution curve. Okay, alright, so dia cerita kat sini, as the absolute temperature increases, the average velocity increases. Ini kita tahu, temperature increases, velocity pun increases. Okay, the average velocity increases. So the distribution function, the graph, we are talking about the graph. Okay, distribution function spread out, maksudnya merebak. Okay, merebak membesar, pelik ni. Spreads out maksudnya dia mengembang ke sebelah kanan. Okay, because dia bukan sebelah kiri, sebab sebelah kiri dia start daripada starting point, the same starting point. Dia merebak, spreads out, dia merebak ke sebelah kanan lah, resulting in more molecule with faster speed. Okay, cuba tengok graph ni. We have number of molecule on y-axis and versus molecular speed on the x-axis. Okay, alright, tu still sama dengan normal graph kan. Okay, kenapa graph tu dia macam ni? Okay, dia macam bukit-bukit ni. Alright, what does this represent? Kenapa in terms of bukit? Okay, luas bawah graph. Okay, dia punya area bawah graph tu represent, you kena tahu dia represent apa. It represent the number of molecule. Nampak ni? So number of molecule ni adalah bersamaan dengan luas bawah graph. Okay? Alright, so we are talking about nitrogen dekat sini. The same gas but at different temperature. Okay? Nitrogen at 100K Kelvin and then nitrogen at 300K and nitrogen at 700K. They are all having the same luas bawah graf. Okay, dia punya luas bawah graf ni sama tau. You nampak je tak sama. Seorang ke atas, seorang ke bawah, dia landai sikit ke tepi. Yang ni lagi landai. Okay, but actually dia punya luas bawah graf adalah sama. Sebab kita nak compare, mestilah compare ada benda yang kita fixkan, ada benda yang kita varies, kita ubah-ubah. So in this case, yang kita fixkan would be the type of gas dengan the number of molecule. Ini number of molecule dia. Okay, so katakanlah number of molecule dia 300 molecule of nitrogen. 300 molecules. What we varies, kita varies in terms of temperature. Okay, so as you can see, nampak tak apa bezaan dia tu? Bila temperature increases, bila 700K, dia punya graph tu jadi landai. Yang ni meninggi kan, yang ni jadi makin landai. Kenapa makin landai? Sebab more molecule, luas bawah graf more molecule will have higher molecular speed. Nampak? Pergi ke kanan, the speed become higher. So lagi banyak molecule having higher speed ataupun faster speed compared to yang tinggi 100K ni. Okay? Dia punya nampak speed dia kat kawasan molecular speed yang rendah. Same goes to this one. Yang tengah ni, yang 300K ni. Dia punya speed dia tu banyaklah yang lebih tinggi daripada 100K. Okay, tapi taklah sebanyak 700 Kelvin. Okay, hope you guys understand that. Faham yang tu. Okay, serabut. Okay, so ni kita cakap pasal number of molecule. Imagine kalau dia punya number of molecule ada 300 molecule. Okay, luas bawah graf dia. So they differ in terms of the temperature. Jenis pun sama. Jenis gas dia adalah nitrogen. Okay, alright, cuba tengok yang kedua punya graph here. Okay, sekarang ni kita varies in terms of the type of gas yang kita ada. So kita ada chlorine, nitrogen and helium. Okay, alright. So sama juga number of molecule can be represented dengan luas bawah graf dekat situ. Okay, versus molecular speed. As you can see, helium dia punya lagi landai dekat situ. Starting point dia sama. Okay, kalau you are asked to draw, make sure that you start from the same starting point. Tapi dia punya ending point dia berbeza. Okay, so it shows that helium having more, nampak tak? Dia punya molecular speed dia tu. Banyak yang tinggi-tinggi. Kenapa? The reason being is because of helium is lighter, paling ringan. So kalau lagi ringan, by right, the velocity will be higher lah. Okay, compared to chlorine. Chlorine berat, 70.9. Nampak tak dia punya coverage of velocity dia tu? Coverage of the velocity is around this area saja, around this one, 500 ke 600, 700 ke macam tu. Okay, which is slower lah. So they move slower compared to nitrogen and helium. So helium is the lightest, yang paling lightest. Okay, so the lighter molecule are moving faster. Okay, tapi temperature dia remain constant. Temperature remain constant. Yang berbeza dari segi dia punya what they call that, dia punya jenis gas dia. Okay, alright. So make sure you faham dia punya Maxwell Boltzmann, sebab ni antara famous question. Dah beberapa kali berturut-turut dia keluar. You are asked to draw to represent the Maxwell Boltzmann distribution. Dia bagilah condition dia tu at temperature 200, 500 and 1000. Okay, show how the Maxwell speed distribution curve yalah, kena show lah. Okay, alright, so we have checkpoint 12. Okay guys, so please complete this checkpoint. Okay, so the time is up. Okay, alright, so that's about it. Any questions? So please complete this checkpoint. We will discuss it tomorrow. Okay, any question related to the topic?